okay? Yes, amplified. So we were busy discussing prediction for the Drell-Yan process, for the proton-proton process, but through the rules of the Parton model, we could change the problem to computing the quark-anti-quark annihilation to a lepton-anti-lepton pair. And to get to the proton prediction, we just have to multiply with these Parton distribution functions, integrate over the momentum fractions. I'll see it's not in the notes I gave you. I'll see if I have some notes on the Parton model elsewhere that I can just send you even as a PDF or so. It's sort of separate from the notes that I gave you. These will be just a bit of text and a few expressions and pictures, but it's not a long calculation. Good, so that's the assignment. We have these files that we can download, and our job then is to compute this. And this is the Feynman diagram. So we have momentum P1, P2 coming in, Q and going through the photon, and Q1 and Q2 going out. And remember, these are quarks and these are leptons. So although many of you may have seen this, I thought maybe I'll go a little bit in detail through computing this diagram, particularly its absolute value squared, because that's necessary for the cross-section. So the scattering amplitude or the invariant amplitude I call M. Now, by the Feynman rules, just see if you can follow, there's a factors of I 2 pi to the fourth. There's one propagator here in the diagram, from here to there. That is a 1 over I 2 pi to the fourth. There are two vertices, each with an I 2 pi to the fourth. So the net, there's an overall I 2 pi to the fourth. There's also momentum conserving delta functions here that you can get rid of, such that there's only one overall momentum conserving delta function left, namely the delta function, a four-dimensional delta function of P1 plus P2 minus Q1 minus Q2. Now the rules, if you look in field theory books for computing this, is that you always must extract an I 2 pi to the fourth and one overall momentum conserving delta function. That you sort of extract, and what's left is M. So I ignore the momentum conserving delta function and the I 2 pi to the fourth. Okay? So let's just follow the rules and see again. It's a game of salmon. You swim upstream. So let's start with the lepton part here. So we write M is U bar of momentum Q1. U bar, this is also in the appendix of the notes. U for fermions, V's for antifermions. And U bar, you start with a row, matrix, matrix, column. That way you get a number. And so we start here with a U bar, a row spinner of momentum Q1. Then we arrive here. And that is just minus I gamma mu, minus IE gamma mu. And then we're already here, and that will be a V spinner, because it's an antifermion of momentum Q2. Of course, these all have spin labels too, and let me call them S1 prime and S2 prime. These are the spin labels. Then we have the propagator. Actually, let me do this one first and leave a bit of space. Then we have here V bar of P2 minus IE QF gamma nu U of P1 with momentum S1 and S2. So that's for this fermion line. I start here with a V bar and go down all the way down to U. Right? And you see here it needs row spinner, matrix, column spinner. That way it's really a number. The only thing we haven't accounted for is really this propagator. And there I just use eta mu nu divided by Q squared. That's momentum going through this line. I set this lambda parameter equal to 1. In fact, it didn't even have to do it, because if you would compute it, if you would keep the lambda there, there would be K mu, Q mu, Q nu term. That would be 0 by Ward identities, if you happen to know what that is. But one way or another, I can be set to 0. So this is it. Notice also this factor QF, because this is the interaction of the photon with the quarks. And the electric charge of the quark is not necessarily 1. It can be 2/3 or minus 1/3. And so QF is either plus 2/3 or minus 1/3. There's one final factor missing. Who has an idea? It's a bit of a trivial factor. No, that I've gotten rid of. I don't need an I 2 pi to the 4th. Is it, someone said some index or so? No, the coupling constants are here, E and E. Sorry? It's a delta. It's a Kronecker delta that's missing. Of what? No? Colors. That's very good. So these, the leptons I don't have color, but really I should write here also a color index I and J. So I really should write here delta IJ. It's a bit of trivial. No color gets changed. It's all electromagnetic interactions. So, and recall our definition that we have Q squared is minus S hat. And Q squared is negative, S hat is the collision energy squared. Now, have you seen such identities that U of P, U bar of P, S, S is minus I P slash plus M? Completeness relations for the U's and the V's. And I use that when I square this amplitude. And something similar for the D's. Except in this case, M's a 0. I assume that the leptons are massless and the quarks are massless. So there was no M here, it's just this. So, and then you get the sum over S1, S2, S1 prime, S2 prime, all these 4 fermion spins of the absolute value of M squared is, and this is from field theory courses, is equal to e to the 4th QF squared 1 over S hat squared, and then trace of gamma mu P1 slash gamma nu P2 slash times the trace of gamma mu Q2 slash gamma nu Q1 slash. I should really actually have called this mu prime here and this mu prime. It doesn't matter really, but if I take M times M star, then in M star I would use nu prime, and this is what mu nu then are. The mu is from the M and the nu from the M star. So these are traces over these gamma matrices. Whenever you've seen such steps, it's always a little bit of work, a few lines of work just to, but I see many of you nodding that this is known. Okay, this has to be worked out further, but once you have, you need to use it somehow. So for the cross section, how you use this expression, whatever it will be, well, let's see if we can remind ourselves of the formula. First, we need to integrate over all of the phase space, 2 pi cubed to omega 1, integral d 2 pi cubed to omega 2. Then we have 2 pi to the 4th delta function of P1 plus P2 minus Q1 Q2. Then we have the sum over the spins of m squared. That's the thing we just wrote this expression for. So that's the integral over the final state phase space of the two leptons and the absolute value of the matrix element squared. That's how the recipe for a cross-section works. There's a few factors missing in front. Well, let's see if we can construct them. So what is missing? Who happens to know? If you happen to know. Not something that you can derive from the previous formula, you just happen to know it if you have computed cross-sections before. Flux factor, right? That is 1 over 2 s hat. That sits there. Anything else? That is a flux factor I will not explain. I'll just give you it as a recipe. An actual initial spin, so I get for that 1 over 1/2 squared, right? So you get 1 over 2 squared. Anything else? 1 over initial colors, so we get 1 over NC. But we must also sum here actually over colors, C. And that is a factor NC. NC is the number of colors, really 3, but I told you I would do this. I would keep the parameter clear. So this is just because for up, anti-up, I can still have this coming in 3 colors, so I sum over it. But I actually also average over it. There's a 1 over NC squared here, sorry. 1 for each incoming quark, and then I sum over them, it gives an extra factor NC. So it certainly looks like a bit of a formidable formula. I had an aside on gauge fixing, but I think from what I could understand, I can skip that. Right? So let's see what this becomes. So first of all, this thing. There's an NC here also. Let's first write this thing. I can take the traces, that's identities for them, you can find them in the notes. You can combine them all, and this is the answer. So sum over the spins of m squared is 256 pi squared alpha squared qf squared over s hat squared times 2 times p1 dot q2 p2 dot q1 plus p1 dot q1 p2 dot q2. So not too bad, right? You normally this gives you 3 terms, and this gives you also 3 terms, and when you combine them, it's not too bad. Alpha, how does alpha squared and pi squared come in? Who has an idea? Right, so you just use that. Indeed, e squared you can write as 4 pi times alpha. You also see 1 over s hat squared from the photon propagator squared. It gives you 1 over s hat. So nice. And now we must integrate over these momenta q2 and q1 to 4 momenta. And p1 and p2 are fixed. Right? We have the final state momenta we must integrate over using, well, such a formula. Now, this is certainly doable, and some of you may have done this already. Ever done this? Somewhat? No one? Some of you have. So the classical way to do it, I'll give you a bit of a quick way. The classical way to do it usually is, in almost all cases you have to do it that way, is that now it's all still covariant, but once you need to do the phase-space integrals, you need to choose a frame. Then you use that the beams come in along the z-axis, you parameterize things with cosines and thetas, and you integrate over that. And that certainly works, and is certainly something I would recommend. It's a bit plodding along, so I like to do it in a bit of a quicker way. So usually the phase space integral done. The phase space, I will often abbreviate it as PS, not PostScript. The PDF and PS, but again an overloaded concept. Phase space integrals done by choosing a frame and parameterizing the momenta. So you would then pick P1, for example, to be the square root of S hat over 2 times 1, 0, 0, 1, and P2 to be square root of S hat over 2, 1, 0, 0, minus 1. And then Q1 you would put in some direction with a polar angle theta, and Q2 must be exactly opposite that. It's a 2 to 2 process. The momentum of Q1 must be exactly opposite the space part of that of Q2. And then you can integrate over these angles. I will use something called Lénard's identity. This is a bit of a trick. I guess I will erase this. Which you may want to prove in the tutorial session for yourself. It's a nice exercise. So here we can use instead of PS integral of Lénard's identity. And it says the following: d4q1 delta of q1 squared d4q2 delta of q2 squared delta 4 q minus q1 q2 times q1 mu q2 mu. If you would have to integrate that with these two vectors here loose, this is equal to pi over 24 q squared eta mu nu plus 2 q mu q nu, where q is the sum of these two momenta. It's certainly not obvious. But it would be actually, the reason it's simple, but if you for the moment assume it's true, then this combination is the same as d3q over 2 omega 1. Right, so you can write this combination as d3q1 over 2 omega 1. So that corresponds to our phase space integral. For q, we have p1 plus p2. Right. So that delta function we have in our integral. And then here, inside this, we have these terms. So that's q2 mu, q1 u, contracted with something. But I just strip it off and replace it with this formula, where for q, I write p1 plus p2. So then all the q's are gone, and everything is a p1 dot p2 or p2 dot p1. It's the same integral after using the identity, and it's fairly easy to do. And so if you buy the identity, then the integrals are very easy. I don't have to pick a frame. I just plug it in, use it. Is that idea at least clear? I'll give you the answer then in just a second. But maybe I should make a remark as to why this would be true, this identity. Because it appeals to a general principle that comes in again and again in particle physics. So here we have some complicated integral in principle, and whatever the result is, it has a mu and a nu index. And whatever the result is, q1 and q2 cannot occur anymore, because they've been integrated over. The only thing it could be that you could have in the final answer is this momentum q. There's nothing else in the interval. So we need something that it has two indices and has q in it. Well, these combinations, eta mu and q mu are the only ones you can make. So what you do is you write them as arbitrary coefficients and see if you can derive the arbitrary coefficients. And how would you do that? Well, you would contract both sides once with eta mu and once with q mu. And then it turns out, thanks to these delta functions, this integral becomes much simpler. And it can be very quickly done. There's still 3-4 lines, but much quicker than with the phase-space integrals. And that fixes these coefficients for you. If you wish, you can also just verify it by contracting with this in this form and see that you get exactly the same left and right. Is the idea at least clear? Yeah? So the answer then is the result. The total cross-section for QQ bar into leptons is, if I put it all together, 4 pi alpha squared QF squared over 3 NC S hat, where S hat, I remind you, is xi1, xi2, S. So the partial momentum fractions are in there. That's a nice answer. Very simple. One more step remains. So this is just if you wish to verify. That's not very hard. We did it this morning before class. Is to turn this into the differential distribution with respect to q squared. That's what we still wanted to do. And that is just a very stupid trick. So this is the cross-section for for QQ bar to lepton, anti-lepton with any possible final state mass q. Now we want to make a differential in that. So we can write for differential cross-section. We write sigma of S hat. I'll drop the labels because it's more general. Is trivially dq squared delta S hat minus q squared of sigma hat of q squared. You will agree with that, right? The triviality. But that means that this can be seen as d sigma dq squared. Which you can then write as 4 pi alpha squared qf squared over 3 nc q squared times delta 1 minus q squared over s hat. I extracted one factor s hat out of the delta function, and it became an extra q squared factor. So this is the differential cross-section for quark, anti-quark to leptons, the lowest order. The lowest order Brillouin cross-section. Okay. Now, there's a few things to say about this. This variable is very often called z. We'll certainly use z much in the next courses. So z is just the ratio of the invariant mass of the final state leptons divided by the initial state energy squared. The delta function says, look, they have to be the same, which is pretty obvious. The reason that it's so at higher orders, this is not so obvious. For example, you could have, say, next to gluon radiated. I'll just sketch that a little bit. But your initial state energy is larger than q squared. It radiates off a little bit of energy, and then you have enough to make q squared. So z can be smaller than 1. but if you don't have any extra radiation, it must be exactly equal. Z must be equal to 1, as the delta function tells you. Another good thing to remark is a very curious aspect of this formula. We compute cross sections here, which are supposed to be physical things, something you can compute, you can measure. There should be a function, but the delta function is not a function, it's a distribution. So this is a weird thing. How come does it make any sense to have a cross section written as a distribution, something a distribution in the the function sense? It's not a function, right? It's a delta function is something else. Why is that so? No, it's actually much more mathematical than that. It's not. You don't have to invoke experiments for that. Okay, for the answer. It's also true, but it's not the reason for this. So if it was just this as a number, that's fine. I can deal with numbers. But this is a distribution, and that only makes sense when you integrate it with a smooth function, and then it only makes sense. But here it's just a distribution, so it doesn't make sense. But let me ask you this then, to see if it will help you on the way. Is this the cross-section that you really can confront with data? You say no, why not? Sorry? It's a partonic crossing, meaning? Right, so what should we do with this though? You still have to multiply with the PDF functions and integrate over the xi's. So remember, in here sit the xi's. Right? This is xi1, xi2s. You have to multiply this with functions of xi and integrate. So then it's okay. We integrate the distribution with smooth functions, and then we have a number. So it's important to realize that partonic cross sections can be distributions, not always functions of numbers. We'll see this also at higher orders occurring with different types of distributions. Then delta function, we'll see so-called plus distributions. But now we know we don't have to worry, because there's always the PDFs you still have to integrate with, and those are smooth functions, and then it will be fine.
Did this delta function, did it arise in the calculation, or did you artificially?
It arose because I asked for the differential cross section. For the total cross section, it didn't matter. Then it was just a number, right? But because I asked for the differential cross section, the formula I had there had the differential cross section, and then I got the delta function. You may ask, well, why do you make life so difficult? You create problems that weren't there, but we'll need it as an example later. This is the one that people always use. So one thing that we'll consider in the next lectures is higher order calculations to this. So we have here a real emission correction. We will also look at virtual corrections like this, gluon exchange between the quarks, the incoming quarks. All of this QCD correction only happens in the initial state, where the quarks are. You will never have anything with gluons in the final state, because that's what the muons are. They don't couple to gluons. So it is a bit cumbersome to, if you do all these higher order calculations, constantly drag the final state along, the mu plus mu minus. In fact, what happens here, if you look at the picture, this looks like a photon is being produced with mass big Q, that then decays to a lepton, anti-lepton pair. It's a bit of it's an off-shell photon, obviously. It's not massless photon. Photon's a massless on-shell, but it would be an off-shell photon with a mass or a virtuality Q, then decaying. So we might as well see if we can just produce this bit and correct for the rest with a factor. That will be true for all orders in QCD, because whatever I do with the initial state, it's always this simple decay. So can I write sigma q bar to mu plus mu minus as some factor k times sigma of q bar goes to gamma star of mass q. So this gamma star means an off-shell photon, and q is then the off-shellness, the virtuality, the mass of the photon. And k just then is some factor that corrects the rest. In fact, this would be for d sigma dq squared. D sigma dq squared. And the answer is yes, otherwise I wouldn't have asked the question. And k is yes. K is 2 pi alpha over 3 pi s hat. 2 alpha over 3 pi s hat. So indeed, one alpha is removed. You remove the decay here. Also, you don't take care of the propagator anymore, so the 1 over s hat goes, a pi goes, so not too surprising. So that's the only intuition you can have. So for the future, if I look at Brillian, I will not look at lepton decays. I will just think about producing an off-shell photon. And then the lepton decay I can always slap on at the end with this factor k. As you can tell, we particle physicists are very lazy. We always try to do things quick and dirty. And what time did I start? Sorry? Okay, so about 15 minutes. I think start a bit after 11, I think, right? So this is a process that is pure electroweak at lowest order, electromagnetic even. Let me, without going through all the calculations, at least give you the result for a similar process that looks whose formula also looks similar. Is also important at the LHC. Similar process to Brillian. Would be proton-proton goes to top anti-top plus x. Top is a very heavy particle. And so we neglected here the muon mass, we neglected all the masses. We can't do that there. We need to include the top mass. So again, to make that prediction, we use the parton model again. So in our minds, we have these PDFs ready to multiply our partonic cross-section and integrate. All we need to do is to compute the partonic cross-section for parton to TT bar. So the partonic processes are quark anti-quark, quark anti-quark goes to a gluon, go to a top anti-top. That's at lowest order the only process you can make if you have quark anti-quark in the initial state. You see the similarity to the diagram we had before, but also some differences. You see here that the particle now is a gluon, the quark's initial and final state. These things have a mass, but I can give you the cross-section. It looks very similar to what we just had. So the cross-section for QQ bar to TT bar as a function of S hat. Here I will just give you the formula for this. I will not do this thing, the differential one, just this formula. And the result is 2 pi alpha s squared over 3 s hat CF over NC square root 1 minus 4m squared over S hat 1 plus 2m squared over S hat. So again, a nice short formula. You see also the appearance of M, the top quark mass. And I wanted to give it also to you to.
Problem with the system, he's fixing it. The camera.
Oh, okay. So yeah, this is also very interesting. Maybe more interesting than this.